Hello, we're going to be looking at temperature today, and before we talk about temperature, we should probably know what temperature is. So let's look at a definition for this. And we're going to get a better definition than this later, but for now, this will help us get started. Temperature is how hot or cold something is compared to a reference. So if I have something, say this pen, and I want to know its temperature, I would compare it to something else and say, is this pen more hot or more cold than that object? If we want to get more technical about this and take numerical data, we have three different options for scales we can use. And you do need to memorize the names of these three scales and the melting point and boiling point of water in each one. So let's go through each one and see where it's used and some details about it. The Fahrenheit scale is used primarily here in America and really nowhere else. There may be a few countries scattered here and there that use Fahrenheit commonly to measure temperature, but the United States is pretty much it, mostly because we're stubborn that way. So the Fahrenheit scale, it's abbreviated as degrees Fahrenheit, so degrees symbol, then a capital F. And in this scale, the melting point of water is 32 and the boiling point of water is 212. Notice how difficult that is to remember. On the Celsius scale, that's degrees and then capital C, the melting point of water is 0 and the boiling point of water is 100. This is the scale that's used primarily throughout the world just for common measurements of temperature. Notice that it makes a lot more sense with the melting point and boiling point of water being 0 and 100 respectively. That's really easy to remember. Makes this scale very nice for measuring the range of temperatures that you encounter in everyday life. And then the last one, Kelvin, is the temperature scale that scientists use. And scientists use it as opposed to the other two for a very specific reason. With Fahrenheit and with Celsius, it's possible to have negative temperatures. That is, if you're below the melting point of water and you're dealing in degrees Celsius, you're going to be dealing with negative temperatures. With the Kelvin scale, however, there are no negative temperatures. Instead, the coldest temperature possible, called absolute zero, is 0 degrees. So there are no negative numbers at all, and the bottom of the scale corresponds to the coldest possible temperature, which there is in fact the coldest possible temperature. How strange is that? We'll talk about what that means in a moment. And so on this scale, Kelvin has exactly the same size units as degrees Celsius, so 1 Kelvin is the same size as 1 degree Celsius. And the melting point of water in Kelvin is 273.15 Kelvin, and the boiling point is 373.15. Notice you don't have to say degree with Kelvin. And again, Kelvin is the scale used by scientists around the world. All right, now that we know that, I want to dive in to the mechanism of temperature a little bit deeper and kind of get you an idea of where this is coming from, and we'll come back to this idea of absolute zero, the fact that there's a coldest temperature possible. So for a second definition of temperature, this is a more technical one. Temperature is the average kinetic energy of the molecules of a substance. We should probably unpack that a little bit and see what this means. So first, let's start with energy and what energy is and what that means. Energy is the ability, and if I was really fancy, I would spell ability correctly. Temperature is, or energy rather, is the ability to cause a change in motion of an object. So basically, if something has energy, it can change the motion of something else. Now, whether it does that directly or through other means is beside the point. But energy is just this way of saying that an object is capable of changing motion in something else. And particularly when we talk about kinetic energy, we're talking about energy that is due to motion. That is, an object has the ability to cause a change in motion because it itself is moving. And the way it works for kinetic energy is this. It depends on two factors, the mass of the object and the speed of the object. The more mass an object has, the more kinetic energy it has. Also, the more speed it has, the more kinetic energy it has. So the faster it's moving, the more kinetic energy it has. And temperature is the average kinetic energy of the molecules of a substance. So let's take a look at what that means with this nice little simulation. So here I have a container full of neon gas, and each atom of neon is represented by this little blue dot. The temperature of this, which you can see, it's got a thermometer here, and it's telling us that the temperature is 55 Kelvin, which is really, really cold. But the temperature is a measure of the average kinetic energy of these these atoms rather, that you see in here. And notice that that depends on two things, mass and speed. All of these have the same mass, so really what it boils down to, if you're going to put this all in a nutshell, is that temperature depends on the speed of the atoms or molecules in a substance. And notice they're not all moving at the same speed. Like if you watch one of these, some of them are moving kind of slow, others are moving fast. So it's important that we take the average speed. If we take just the most common one and find that. We can play around with this idea that the temperature is dependent on the kinetic energy, which is dependent on mass and speed. I'm going to not change the speed of these at all, but change the mass, and I want you to watch what happens to the temperature. I'm going to go from neon to argon. Argon is heavier than neon, and I want you to watch what happens to the temperature without speeding these up. Just by changing to a more massive type of atom, the temperature has gone up. Now the other way to do this, when I heat something up, what I'm really doing is I'm causing the molecules or atoms in it to move faster. So as I heat this neon, and if we were to watch this very closely, as it gets warmer and warmer, on average, these atoms are going to be moving faster and faster and faster. On the other hand, if I were to cool them down, as they get colder and colder and colder, they move more and more slowly. And this is where that idea of absolute zero comes in, is that if I cool this down to the point where these atoms are not moving at all, that would be 0 Kelvin, the coldest temperature possible. All right, I've rambled on for a bit here. I do want to get this in as maybe the last thing you see on this video. The faster the molecules of a substance move, the higher the temperature. And the other side of that is true as well. The slower they move, the lower the temperature. And this, in fact, is the big idea for temperature. If you remember nothing else, that temperature is the average kinetic energy, which is based off of speed. The faster the molecules move, the higher the temperature of the substance.